Hello, dear friends. This is Dr. Pramod P. And today we will discuss an interesting topic that is synchronous counter design using JK flip flop. So, let's start with the design of a 3-bit synchronous counter. 3-bit synchronous counter requires 3 flip flops, and flip flop is a basic memory unit and which can store 1 bit at a time. And we need 3 such flip flops. We have 2 data inputs over here, J and K, and clock is used to trigger the flip flop, and here it is positive edge triggered. If there is a bubble in front of that triangle mark, then it is actually negative edge triggered, but there is no bubble over here, so it's a positive edge triggered flip flop. Q and Q bar are the outputs. We may have sometimes clear and preset inputs also. They are asynchronous inputs. They are basically used to change the normal flow of counting sequence. If clear is activated for a particular flip flop, then its output Q becomes 0. That is, it is in a reset state. And if preset is activated for a particular flip flop, then its output Q will be equal to 1. That is, it is in a set state. And we can combine all the preset together and clear together. Then we can have the entire control of the counter, and thereby we can change the normal sequence of operation. The truth table of JK flip-flop is shown over here. We have the combinations for J and K respectively 0, 0, 0, 1, 1, 0, 1, 1. Then the corresponding Q and Q bar outputs are Q for 0, 0, input J equal to K equal to 0. The output remains at no change. So it is NC, but it is normally indicated as Q bar. That is no change. Then if the input J equal to 0 and K equal to 1, that is exactly reset state. That is Q is equal to 0 at that time and Q bar equal to 1. And for 1 0 the combination, the output Q will be equal to 1 and Q bar will be equal to 0. That is set state. And finally for 1 1, the combination 1 1, that is J equal to K equal to 1, and the output state is normally toggling. Output will be in toggling mode. That is, it is usually indicated as Q bar and Q, and it is Q and Q bar for no change. That is for J equal to 0 and K equal to 0. So that's all about a brief explanation of JK flip-flop and how it produces its outputs. Now let's proceed with the design of a synchronous counter, and for that at first we need to write present state. Present state, we have 3 flip-flops outputs Q2, Q1, Q0, where Q2 is the MSB and Q0 is the LSB. This is followed by the next state combination, and they are Q2 dash, Q1 dash, and Q0 dash. And next I am writing the combination of inputs required, and we need to have the excitation table for JK flip-flops also. And here it's a truth table actually indicating all the combinations, and that is present state combination, next state combination, and how to derive inputs. That is, we have 3 flip-flops, means as far as JK flip-flops are concerned, we have 2 inputs. Therefore altogether we will be having 6 inputs. They are respectively J2 K2, J1 K1, and J0 K0. Now let's fill the table with zeros and ones. That is for present state, starting with 0 0 0 and finally 1 1 1, because it's an up counter, right? So with the 3 bits we will be having 2 raised to 3 equal to 8 combinations as indicated here. And now moving on to the next state, 0 0 0, the next state is 1, that is 0 0 1. So we need to write the next state of the present state 0 0 0. So that is here it is 0 0 1. So and for the next combination, that is present state 0 0 1, the next state is 0 1 0. So accordingly we will fill the table this way, and after writing all the next state combinations, let's recall the excitation table for JK flip flop. Then only we will be able to proceed as far as the design of inputs are concerned. Excitation table of JK flip flop is given over here. That is Q bar, and here uh, actually this is present state and next state. Listen, here Q dash is not indicating Q complement, but it is indicating next state. If the present state is 0 and next state is 0, what will happen? Likewise, we have with Q and Q dash, we will be having 4 combinations, that is 2 raised to 2 equal to 4. The first combination is 0 0, that is if the present state is 0 and next state is 0, what will be the JK input combination? It will be 0x, and if present bit is 0 and the next bit is 1, it will be 1x, and if it is 0 respectively for present and next state, it will be x1, and if it is 1 1, then it will be x0, and here x represents the don't care. Now let's proceed with the truth table for the first combination, that is 0 0, it is 0x for J2 and K2, and for J1 and K1 it is 0 to 0, the change again 0x, and for J0 and K0 the combination is 0 to 1, so it is 1x. Then for the next row 0 to 0, it is 0x, then 0 to 1 it is 1x, and 1 to 0 it is x1, and similar fashion we can fill it for all the remaining inputs. Now let's try to obtain expressions for j and k inputs. Let's start with the j2. Yeah, it's a 3 variable Carnot map. Over here we have inputs q2, q1, q0, q2, q1, q0 splitted like this. Yeah, this is what you will be getting, and yeah, for don't care terms and 1, you can group 1 and x, the don't care, together like this to form a pair. So the common variables over there are q1 and q0, so the expression is q1 and q0. Now the k2 input of the most significant flip-flop, yeah, as usual, k-map, Carnot map, it's a 3 variable Carnot map. Q2 splitted as Q2 towards left side, towards right side, Q1, Q0, combination 0, 0, 0, 1, 1, 1, 1, 0, which follows gray code ordering. And yeah, we have 4 don't care terms over here, and only a single 1 and 3 zeros, so that we can group 1x, that is don't care, and 1 together. So the expression remains the same as q1 q0, so we can conclude that over here for the MSB, that is most significant flip-flop, over here we have J2 equal to K2 equal to Q1 and Q0. Now for J1 and K1, let's proceed, and you will be able to group it this fashion. For J1 you will get Q0, and for K1 similar fashion, but there will be change in positions of don't care and ones. Anyway, the grouping will be yeah, the group will be a quad, so again it's q0. So here also we have j1 equal to k1 equal to q0 or q0, so that is the second expression. Then the third flip-flop, for that the j input is j0, and q2, q1, q0, that's a split of variables for Carnot map. Then 0 0 0 1 1 1 1 0 written over there. Then let's fill it with the ones and don't cares. Then yeah, then you will be able to find yeah, all the 8 cells are filled with either 1 or x, so we can group everything together to form an octet. So if we are able to combine a single group consisting of all the elements in a map, then the value is equal to 1. So here cannot exactly the same, the result is, but the positioning of x and 1s will be slightly different. Yeah, anyway it will be x x1 1 x like that for the upper, and towards the bottom row also it will be x1 1 x. So again ones and x only, don't care, terms only. So it's filled completely with either 1 or x, so the result is again 1. So here we can conclude that our expression is j not equal to k not equal to 1. We have now all the expressions, 6 expressions for 3 flip-flops. Let's proceed with the block diagram. And here we will be able to find it's a synchronous counter. So we need to give the clock pulses together to all the flip-flops. Then to start with, yeah, let's connect the inputs. J0 K0 equal to 1, so it is connected to 1, and clock is given CLK, and Q naught and Q naught bar are the outputs. And listen, these are synchronous counters, and the synchronous counter means all the flip-flops will be triggered simultaneously. As already mentioned, if it is positive edge triggered, then the data will change during the positive edge, and if it is negative edge triggered, the data will change during the negative edge. And this is the second flip-flop written over. Then yeah, the clock of the first is given to the second also, so that both will be getting triggered simultaneously. J1 K1 are the inputs, K1 Q1 and Q1 bar are the outputs, and J1 equal to K1 equal to Q naught is the expression we got, so accordingly it is connected over here. Then the third flip flop, or we have inputs J2 K2, then Q2 bar are the outputs. Then we need to connect the remaining. So we have the clock, yeah, clock input, yeah, it is connected. So all the three have a clock from the same point, so simultaneously triggered. And now let's see the expressions. We got j2 equal to k2 equal to q1 and q0. So we need an AND gate over there. So q0 and q1 connected, yeah, then yeah, like this. And finally we got our synchronous up counter. So this is usually simple. The design is we can design it by using D flip-flops and T flip-flops also. Hope all of you may have understood this design of synchronous up counter, 3-bit up counter. And yeah, hope you may have well understood the design part. Thank you all for watching this video. Have a nice day.